Okay, gang, welcome to CSC 475. Believe it or not, we're getting close to midterm. Our midterm is going to be on Tuesday, a week from today. So we're actually starting to get close to being halfway through this quarter, believe it or not. So that's actually what I wanted to start with, was to talk about the exam. To begin with, I have 3 people that I know of that are graduating as seniors. That's Bignell, Kaysen, and Holland. Those are the 3 that I know about. If you are a graduating senior and I did not list your name, Bignell, Kaysen, or Holland, send me an email so I can get you on the list. As I mentioned, I think on the first day, I'm not planning to give the final exam early. The final exam will be the last day of class. And what I do for graduating seniors is I'll turn in a grade estimate. Usually, it's pretty easy to tell based on everything except the final, what a person's final grade is going to be in the class. And because by that time you've earned most of the points. If you are an honors graduate, be sure to let me know that, because like if you were a 4.0, I certainly wouldn't put in an estimate of a B unless it was just almost certain that you were going to earn a B, because I wouldn't want to destroy your 4.0. So get in touch with me if you are a graduating senior. Also, for the exam that's coming up, I have one student that I've talked to about COVID-19 accommodations. My memory tells me that there were 2 of you in this class that had gotten COVID-19 accommodations. The only one that I'm aware of that I've been talking to, you are the student who ends in number 402. You and I have been talking about your COVID-19 accommodations. But again, I seem to have a memory that there were 2 of you. So if you have COVID-19 accommodations, you need to get in touch with me. Probably what we will do is we'll work out the details in email, but you'll probably end up taking the exam online. So yeah, one other student, I thought there were 2 of you, sent me a private, please email me so we can take care of that after class. Thank you, so that we can get that set up. Also, I have one student ending in student number 093 that has testing and disability services accommodations to take the exam over in the testing center. And I've been in touch with that student. If you are a student whose number does not end in 093, and you also have testing accommodations, so we have COVID accommodations and we have testing accommodations for lots of accommodations. Please get in touch with me so that we can make arrangements for that by email. And we need to get those taken care of, especially if you have COVID accommodations. I need to know that those are in place so that we can lock down exactly how we're going to do the exam for you guys and girls. Okay, any other questions about that sort of thing? Okay, as is my normal way of doing business, I have put out a study guide for the exam. And Here is what it looks like. Basically, the study guide is an old exam. This one dates back to 2017. And I give out a study exam for the midterm. I do not give one out for the final. I give one out for the, my finals are private. I give one out for the midterm because I want everyone to kind of have a feel for how I question, what kinds of questions you can expect, etc. So basically, this is a grading key that I used to grade the exams way back in 2017. But the material's been fairly steady. There's some new stuff that could cause things to change. Probably one of the most important things that you want to know is that I do allow one 8.5 by 11 single-sided, quote, cheat sheet that you are free to consult during the exam. That's the only thing, the only notes that you're free to consult during the exam is your single page of 8.5 by 11 cheat sheet. It has to be handwritten and not be typed. I don't want you guys, shrinking all of my notes, to one 8.5 by 11 page and having a magnifying glass so that you have everything there. And it is important that it be handwritten. I don't want to encourage people to, type up notes and pass them around to other people. I want them to be handwritten so that you put in the time to create your cheat sheet. Now, why am I doing that? One is because there are a bunch of formulas, right, and equations that you need to know for perceptrons and for neural networks. So there are computations that you'll have to do on the exam, and I don't mind you having those equations written down. As long as you know how to use them, that's what's important. So I allow that, but the process of creating that cheat sheet, as I call it, is actually the process of studying for the exam. So, so I think that it's a good way to help you study for an exam. But by the way, I hear at least one student who's not muted. I hear you breathing heavily in the background. So if you could check and make sure that you're muted, that would be great. Thank you. So yeah, cheat sheets are important. I like them because I think that they help you study. In fact, when I was a student, I would always make a quote cheat sheet, even if I wasn't allowed to use it on the particular exam, because I found I called it my condensed notes. If I could condense everything important down to one 8.5 by 11 sheet page, I normally found that I do quite well on the exam that way. And I didn't even need it written down on paper in front of me. After I'd created it, I kind of knew everything that was on it. So I could remember it for, I'd look at it right before the exam and cram it all in, take the exam, and then flush that down the memory tube. But anyway, it's a good way of studying for the exam. Okay. So, so what are some of the kinds of questions? There will be a section on the, all of the stuff about the overview, the history, the implications, the potential. On this exam, it was 40 points. That sounds about right. 35 to 45 points, a little less than half. And it can be any kind of questions. So they can be fill-in-the-blank questions, like question number 2 is, state the first law of robotics. We talked about Isaac Asimov and his 3 laws of robotics on the first day. Well, the first law is a robot may not injure a human being or through inaction allow a human being to come to harm. We talked about the paperclip maximizer, Nick Bostrom's example where you build an artificial general intelligence that becomes super intelligent, and its goal is to maximize paperclips so it kills everybody and turns the whole universe into a paperclip machine. about the Dartmouth conference in '56, weak AI versus strong AI. There's normally at least one question about those in some way because they're so important. Describe an objective test to distinguish between weak AI and strong AI. I love questions like this. The answer is there is no such test. So I might give you a question like that the answer is, well, that doesn't exist. That's fine. If you really know the material, you'll have no problems answering that. You have to be pretty certain though. We talked about Doug Linnett and his psych project a little bit, right? He's trying to capture all the common sense knowledge. We talked about Raymond Kurzweil and his singularity. We talked about symbolic AI or classical AI or good old-fashioned AI and machine learning. And then the second part is perceptrons and neural networks. And I ask you some questions, historical about where do they come from. In 1957, blank developed the perceptron learning rule. Well, that was Frank Rosenblatt, right? We call these neurons McCullough-Pitts neurons. So you should know about Warren McCullough and Walter Pitts. And then after that, we get into sort of computational questions. Like in certain instances, such as when weights are not properly randomized, a perceptron may fail to converge on a solution, even if such a solution would be learnable by the perceptron under other instances. And that's false, obviously. One of the best things about the perceptron learning rule is if the perceptron can learn it, the rule will be able to teach it. Doesn't matter what your initial weights are, etc. And then I have you do some computations about perceptrons. Question 20 deals with, how you modify the weights of perceptron according to the perceptron learning rule. 21, make sure that you understand what it means for problems to be linearly separable. And then the last problems deal with computations. We're going to be talking about these kinds of computations today. They are the computations from backpropagation that allow you to compute bias gradients, etc. And so that gives you an idea of what's on the exam. Don't worry about some of these are in red, some of them are in black. The red ones were, I was just getting ready to make the next year's exam, the 2018 exam, and I was deciding what questions I was going to throw out and which ones I was going to just modify. So that's what we have got there. So questions, let's see. The exam will be in person for everyone who does not have accommodations. So other questions about the exam? So so I have it announced here at the top. Exam 1 will be given a week from today in person in either IESB 216 or 218. My understanding is those rooms have been, the divider between them has been retracted, so the rooms are combined. And this study guide that I just went over, that old exam, that's been posted to Moodle. So that's up on Moodle under study guide, so it's available for you to look at. I will not be at the exam. I will, Sam Spawn, my graduate student, will be proctoring the exam for me. So be nice to Sam. Don't ask him hard questions. He's just giving the exam for me. He's not there to answer questions about the exam. If you do have a question, probably the best thing to do is to write a note on the exam saying, I had a question about this problem. Here was my question. I'm answering this question assuming blah, blah, blah. It's about the best we can do without me being there in person to answer your questions. I would say jump onto Zoom, but I'm going to be proctoring the exam for the COVID accommodation people online. So I'm really not going to be available. Okay, so so that's the exam. So today we wanted to talk about backpropagation. To do that, though, I wanted to go back over gradient descent, because we had started, and really gradient descent and backpropagation work together. They're hand in glove, and so we've got to be up to speed on both of them. Essentially, what we're going to be doing with gradient descent and backpropagation is the first thing is we're going to quantify the error that's in the network, and then figure out how that error can be reduced. So that's the first thing. What's the error in the network? Which is kind of a side question. The important question is how can the error in the network be reduced? And then once you know sort of the overall error and how it can be reduced, then you have to figure out how you can apportion corrections to the network to reduce that overall error. Okay, and this will allow us to adjust all of the weights and biases. So the first thing that you need for gradient descent is the stochastic gradient descent and backpropagation. We're going to be using these in a way where we have inputs and we have known correct outputs for our inputs. So this is called supervised learning. You have a large number of inputs and you have the right answers for those inputs. And so it's called supervised learning because a human supervisor had to go through originally and come up with the right answer for each of the inputs. So that's why it's called supervised learning, because a human supervisor for your training data labeled it all correctly. So with gradient descent, basically we'll have input vectors, and an input vector in our case for our MNIST data set is a 784 by 1 vector, because remember we have 28 by 28 input digits, right? There's a 28 by 28 little grid of pixels that represents a digitized handwritten number, digit 0 through 9, and so that's going to be an input. So we'll have an input for 5, a handwritten 5, that'll be a 784 by 1 vector. And we're going to call those inputs X. Okay, now we showed last time how you could take an input X and how you could run it through a neural network to produce an output. So every level would generate an output, right? And we called those output A, and the outputs of the very last level, capital L, was a vector A superscript capital L. So A is our A superscript L is the output of the final layer. So in our MNIST, that final layer is going to be a 10 by 1 vector, kind of like we have here, where the outputs that we're going to get, these are all going to be fractional values between 0 and 1. But what we want, we call that Y. Y is what we want. Y is a 10 by 1 hot vector, where everything is 0 except a 1 in the position of the correct digit. So if we were given a handwritten 5 here, this would be the output for it. This would be our Y, right? Category 0, category 1, category 2, category 3, category 4, category 5 has a 1 in it. and all the other categories have a 0. So gradient descent is taking in an input vector x. It's using x to generate all of the outputs, A, the activations, and the activations in the last layer, I'm just calling it A here, but we usually call it A superscript capital L for the last level. So that's the answer that the network generated. And we also have Y, which is the correct answer that you have, the correct label for the input X. Okay? So you need those things. With those things, you're able to calculate, using the backpropagation equations, you're able to calculate a gradient. Now, a gradient, well, there's two things you calculate. You calculate a cost. A cost is essentially an error function. And then you calculate a gradient, which is, if the cost function is called C, this is nabla C. This is the gradient of the cost function. It's basically the direction, it's a vector that points in the direction of greatest change, of greatest increase in the error function, okay? Now, we don't want to increase the error, we want to decrease the error, so we'll flip the sign. We'll go, if we'll go in the direction of, instead of nabla C, we'll go in the direction of minus nabla C. Okay, so we'll be subtracting rather than adding because we want to go in the opposite direction. So if we've got this smooth surface here, you can think of a vector. If you're here at this green ball, well, your vector of greatest change is pointing almost straight up, right? Well, we don't want to go up. We want to roll down the surface. So that's where we'll be doing like a minus nabla, okay? And again, the equations that we have are not guaranteed. They usually work. They move in. They minimize error, but they don't necessarily minimize overall global error. They'll move you to a local minima. If you've got a very smooth surface like this, well, the local minima is the global minima. It's the bottom of this curved sheet here. But most of the time, our surfaces are very uneven with lots of little local minima. The other thing is once we figure out our gradient, right, our nabla C, and we decide that we're going to move in the negative direction, so we're going to, instead of going in the direction of greatest change, of greatest increase, we'll go in the opposite direction, the direction of greatest decrease. But how far down that vector do we go? Well, we'll have a learning rate called eta, and eta will tell us how far to move down that vector. Okay? All right. So what does the gradient descent, the standard gradient descent equations look like? Well, here they are, and let's talk about them. I presented them last time, but I really didn't talk about them too much. If you've got a weight, this is weight JK. Well, what does that mean? That is the weight from K to J, right? From node K to node J. And K would be, say, in level, let's say it's in level 5. J would be in level 6 because the weights go between the levels. So you're going from K to J, because remember, the way we, in our infinite wisdom, the way we arrange these things is the J is the node you're going to, and the K is the node you're coming from. So the weight to J from K, the new weight, will be the old weight to J from K. And then you've got this stuff here. Minus the learning rate divided by the size of the training data times the sum of the weight gradients. So let's think about this equation. This is the way it's written, but why does it exist this way? Well, backpropagation is going to give us a weight gradient for every input. So let's say we only had 5 inputs, okay? Well, you put in the first input, right? And that's going to give you a gradient, right, for every weight and bias in the entire network. So you're going to get a weight gradient and a weight bias, sorry, a weight gradient and a bias for every weight. You'll get a weight gradient, and for every node, you'll get a bias gradient. So if I had only 5 inputs, well, there would be, for every weight from node J to node J from node K, there would be 5 different gradients. They all would point in different directions depending on the input. But what you're going to do is you're going to sum up all of those weight gradients, all 5 of them. Well, then you divide by the size of the training data. In this case, we had 5, right? So the sum of the weight gradients divided by 5 would give you the average weight gradient, the average direction of change that you need to go for this particular weight. And then what do? Well, you multiply, we're multiplying that times the learning rate. That's our little eta that says how far to go in that direction. And why do we have a minus? Because we're not going in the direction, the average direction of greatest increase. We want to go and decrease it. So that's why we're doing a subtraction here. We're going in the opposite direction. So yeah, we write it as learning rate divided by training data size times the weight, the sum of the weight gradients. But we could just as easily have said, you know, learning rate times the sum of the weight gradients divided by the size of the training data. We could have written it that way. It would have been completely equivalent. And that's really where it comes from, because the sum of your weight gradients divided by how many of these things that you've got is going to give you an average weight gradient. So overall my inputs, what's the average of all of those little vectors telling me? Some say go this way, some say go this way, some say go this way. Well, if I average them all out, what direction do I get for greatest change? And then how far am I going to move? I'm going to move by eta, by my learning rate. And, oh, I got to remember, I don't want to increase the error, I want to decrease it, so I'm subtracting. So that's where this equation comes from. You have almost an identical equation for biases. The bias in node J is equal to, the new bias in node J is equal to the old bias in node J minus the learning rate divided by the training, the size of the training data times the sum of the bias gradients. So again, if I had 5 inputs, my node J here, obviously it would be at some level in the full equation, but I'll have a bias gradient for every bias in the network. Well, for this particular node, sum them all up, divide by the training data size, so divide by 5, right? Because you added up 5 of them, you want the average, so you divide by 5. Multiply times the learning rate, that's how far I'm going to go, and remember to subtract because I'm going in the opposite direction of greatest positive change because I want to reduce my error. Okay. What about stochastic gradient descent? The only difference between normal gradient descent and stochastic gradient descent is normally I don't have 5 inputs or 10 inputs. I have tens of thousands or millions of inputs. And if I applied this learning over, if I had to scan through every single input, right, before I made any changes, any updates to my weights and biases, it would take a really long time. So we use the idea of sort of statistical polling, essentially. So if I've got, 50,000 digits that are equally arranged between 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so I've got 10 categories and I have about the same number of zeros as I have of ones, as I have of twos, etc., well, I might just randomly select 10 items from that and count that as a mini batch. And if I train where I grab 10 of my items at a time, right, after every one of these mini batches, I update my weights and biases. So after I have gone through all 50,000 items, I basically have updated my weights 5,000 times rather than just once. And so that's why we use stochastic gradient descent. It works pretty good as long as your mini batches, we call them, are generally representative of the overall population that you're sampling. And since we're sampling randomly, right, we're using stochastic gradient descent, we're just randomly grabbing them, we should be okay. So, and again, I say we should be okay. Well, what's to prevent the fact that I grab 10 of these randomly and they're all 9s? Could that happen? Yes, it could happen. Statistically, if I'm randomly grabbing items, what's the likelihood of that? Very, 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 very low. How many trials are we doing? Over 50,000 items. We're doing 5,000 different updates. So if you've got a very few outliers here and there, that's fine. When you process that outlier, you'll move in the wrong direction. But that's only one of 5,000. So in general, this is going to work real well because most of the time your mini batch is going to be pretty representative of your entire sample, and so it'll give you a result that's fairly close to what you've gotten from the entire sample. And so this allows us to speed things up by orders of magnitude to speed up the learning process. So again, this is pretty much where we ended last time. What is the stochastic gradient descent algorithm? First, you have to randomize the order of the items in your training set. So if I've got 50,000 items, I've got to randomize those 50,000 items somehow. It's best to do it in an efficient way. And then I've randomized them. So then I divide the training set up into equal-sized mini batches. So basically, if I've got my 50,000, let's say I've got 50,000 inputs, and they're in an array, an old-fashioned array. When I process my first mini batch, I take the first 10 items from that array, positions 0 through 9, and that becomes my first mini batch. And then I'll process it, as we'll talk about here. But when I get to my second mini batch, I'll use items 10 through 19. All right? Remember, we randomized them to begin with. So now I'm taking my second batch of 10, and then I'll take my third batch of 10 from 20 to 29, subscripts 20 to 29, and I keep doing this. Now notice very importantly, I'm never reusing an item. Because if you were doing that, it wouldn't be fair, right? So it's not like I randomly reach in and grab 10 items, and then I randomly reach in and grab 10 items. I had to have remembered when my first 10 items I've taken off the table, right? So when I reach my next 10 items, you know, I don't have a chance of reusing the items I've already grabbed, if that makes any sense. It should make sense because, again, the first thing I do is I randomize the order of the items, and then you can think about it as dividing the training set into equal-sized mini batches. Well, there's no work in that if they're in an array and you just always are grabbing the next 10 items from the array, right? But if you do it like that, then you're guaranteed you're not reusing items, which you shouldn't be doing. Okay, step 3, we're going to get to it. Using backpropagation, compute the weight gradients and the bias gradients over the next mini batch or the first mini batch if this is the first time you did it. After completing the mini batch, so after completing the mini batch, after processing 10 items, right, we're now going to go and update our weights. These equations are exactly what we talked about, except instead of dividing by 50,000 items, you'll be dividing by 10 items because you summed up 10 different gradients for the weight 2j from k. You summed up 10 of them, so you're going to have to be taking this and dividing by 10 items. Learning rate is still eta. That's how far you're going to move, and it's still a subtraction because you're moving in the direction to minimize the error rather than to increase the error. And the biases are exactly the same. It's exactly the same kind of equation there. Okay, so now we updated our weights. What do we do next? Well, if there are more mini batches, you return to step 3, where you grab the next 10 items. And you call back propagation with those 10 items. You compute all of the weight gradients and the bias gradients for every single node and weight in the network. You then use these equations to update every weight and every bias in the network. You then go and say, oh, well, are there more mini batches? If so, you grab the next 10. And you keep doing this 10 at a time through all 50,000 of them. And eventually we drop to step 6 here. Step 6 is an outer loop that basically says you're going to have some stopping criteria. If that stopping criteria hasn't been met, you return to step 1, where you're going to begin a new epoch, it's called, and you're going to re-randomize your training set items. And then you're going to go through, divide that into groups of 10, your little mini batches, and then you're going to go through and do the whole thing, same thing over. So steps 3 through 5 are an inner loop that is processing an epoch, that is processing in little mini batches all of your data. And 6 represents an outer loop that goes back to 1, where you randomize your data and then all 50,000 items, if you had 50,000 items, and then you go through again. Okay, so let's talk about backpropagation. Here's the backpropagation algorithm. It's very simple. A backpropagation algorithm takes as input an input vector x. Remember, that's our input, our 784 by 1. It's all of our little pixel values. And it takes in y, which is our one-hot vector of our desired output. And those are the inputs to backpropagation. The outputs are gradient values for each weight and bias in the entire network. So it would be returning, you can think about it as returning a very large data structure that has all of the, just like we have weight matrices and bias vectors, it would be returning gradient weight matrices and gradient bias vectors. So because every weight, you're going to be returning a gradient, and every bias, you're going to be returning a gradient. So it's returning a whole lot of things. Well, how does it work? The first thing you do is using the current weights and biases, which are initially random, along with an input vector x, you compute the activations, the outputs of all neurons at all layers of the network. And this is the feed-forward pass that we talked about last time. I gave you the equations for how you drive input through the network. So backpropagation actually has 2 parts. The first part is the forward pass, where you're taking an input and you're passing it through the network to get all of the activations, including, most importantly, the activations in the final layer, that capital L layer. And then, once you've got that, you begin a backward pass. So step 2, using the computed output of the final layer, so those are the A's, the activations in the final layer, capital L, along with the desired output vector y, this is the label that you want, the one-hot vector that represents the label, you compute the gradient of the error at the final level of the network. I'm about to give you the equations for that, and then move backwards through the network, computing the error at each level, one level at a time. I'm about to give you the equations for that. This is the backward pass. So you give me an input, I generate an output. I then take that output and the desired output, I do a kind of comparison where I compute an error, a cost, and actually compute a gradient of that cost. And then using that, I push that error back through the network, not changing, but computing gradient biases and gradient weights, or weight gradients and bias gradients for every weight and every bias in the network. And then I get my next input and do the same thing. Pass it through to get the answer that it's generating now, the activations. Compare that to the desired activation, and then I compute weight gradients on the way back. And I do that if I have 10 inputs, I do that 10 times. Now, you could keep up with all 10 of those things and return them and do the summation like we showed here, right? Here back in the stochastic gradient descent. So it's like you called back propagation, you know, and it not only returns it returns weight gradients and weight biases, but instead what you could be doing in your back propagation is you could be summing those, right? Because that's what you're going to need, and you'll be passing less data if you do it that way. So in other words, I go through, give you my first example, get the activations, compare it to what I want, and now I compute all the gradients. Well, then when I do it the next time, I could just be adding those gradients to the sum so far, and that way you will have 10 times less data that you have to pass back. So instead of passing back 10 values, 10 gradients for each weight, and remember, we've got tens of thousands of weights in this thing. For each weight and each bias, if you sum them up, you'll be returning a gradient, a sum of the weight gradients for every weight and every bias in the network. So it's just a little bit more efficient if you actually sum these things up here in the back propagation. And then once you're done, you return as output the gradient values for each weight and each bias in the network. So what are these magical back propagation equations? There are 4 of them, but really there are 3. There are 4 basic equations that simplify 3 equations. And they're real easy to understand what these 3 equations do. You've got one equation that'll give you the error in the biases of the final layer of the network. So because in the last layer, I've got not only the output, the activations in that last layer, I also have what I know to be the correct values. I got that from that y vector, right? That one hot vector that tells me what the answer is supposed to be. So in the final layer, I've got an output, and I've got what the correct output should be. So I have both of those things. So I can directly calculate what the bias gradients are, what the error in those gradients, what the errors in those biases are in the last level. I can compute that directly because I have an output and I have a correct, and I have what the output should have been. So I can compare those and I can compute directly there. But what about all the other biases that aren't in the last level? And what about all of the weights, right? I have to have equations for those too. So equation 2 will be the error associated with the nodes with the biases in the intermediate layers. And equation 3 will be the error associated with each individual weight in the network. Okay. So as I said, there are 4 equations, but if you look, I'm about to talk about the equations. Let's look at equation 3. Equation 3 just says that the bias gradient for node J and level L is equal to this delta value for node J in level L. And if you look at equation 1 and 2, they're computing the delta value for node J in level L. So really what equation 1 and 2 are calculating is the bias gradient for node J in level L, right? So That's why I said, yeah, there are 4 equations, but really there are 3, because you could think of equation 1 and equation 2 as computing the bias gradients for some node in some level. The first one is 4 nodes in the very last level. So what does the equation say? Well, before I go through these equations, one important caveat, okay? I'm presenting here equations for sigmoidal neurons, for sigmoid neurons, okay? Equation 1 and 2 will be different if we were considering ReLUs, for example. And don't worry, I'm going to talk about ReLUs next time probably, and I'll show you what the equations would look like for ReLUs. But right now we're not talking about where these equations come from. We'll talk a little bit about why they make sense, but we're not really talking about where they come from in general right now. What I want you to do today is I want you to understand how to compute the equations and have some idea that they make sense, okay? Next time, we'll talk about the equations in a more general format that would apply to any activation function, not just sigmoid, and I will show you what the equations would reduce to for ReLU, okay? So right now, all you need to know is equation 1 and equation 2 is specific to sigmoid neurons, and equation 3 and 4 are general. Well, 3 doesn't really count because it just says, okay, it's the deltas that you're computing are the bias gradients. But equation 4 is general. It doesn't matter what activation function you're using. Okay, so back to equation 1. Let's look at it. What does it say to do? Well, it says if I want to compute the bias gradient for node, I guess that's a J, my eyesight's failing, for node J in level cap L, so the last level. So if I want to compute a bias gradient for node J in the final level, what I'll do is I'll take the output of node J in that final level, and I will subtract from it the correct answer, the Y value at position J, which will be either a 0 or a 1, okay? But anyway, I've got what my output is, and I'm subtracting from that what the correct answer is. So you can see that in a sense, again, we're not going through all of the reasons, the deep math, but you can see intuitively, I'm taking what I'm getting and I'm subtracting what I need, and so that difference is in some sense a measure of the error, right? All right. What did you get? What were you supposed to get? Well, if I take what I got and I subtracted what I was supposed to get, that difference is in a sense the error. It's indicative of the error. Let's put it that way. Okay. And then we do some things here that kind of seem like magic, but that's okay. We then take that difference and we multiply it times the output of that node times 1 minus the output of that node. You might say, why am I doing this? Next time we'll talk about it. Really what we're doing here is this is a derivative of the sigmoid function is what it is, okay? So this whole thing, the first part is the derivative of the cost function, and the second part is the derivative of the sigmoid function. But essentially, while we haven't gone through all of the details, it makes sense that you would take the output, subtract from it the desired output, and then we do some stuff that has to do with the actual output of that node. So again, we haven't talked deeply about the reasons, but the mathematical computation is very straightforward. You want to know the bias in node 5 in the last level? We'll take the output of node 5, subtract from that what the output for node 5 should have been, okay? Then multiply that by the output of node 5 times 1 minus the output of node 5. And that gives you the bias gradient for node 5 in that final level. Okay. It's a straightforward calculation. Secondly, okay, what about these middle nodes? The problem here is I don't know what the correct answer is at this point, because now I'm moving backwards. Okay, so where this is for level L, for the last level, this is level little l, some intermediate level. Okay, so if this in our network we have levels 0, 1, and 2, so I would have been computing the biases in level 2. Well, I would use this for the biases in level 1 because it's a step back. It's an intermediate. It looks a little scary, but it really shouldn't be scary at all, because what it's saying is the bias gradient for node, we're calling it K here, for node K in level L is the weighted sum of the bias gradients in the next level. This is an intermediate level. Let's say that it's level 1, okay? So what I'm saying is if I want to compute the bias gradient for some node K in level 1, I will first multiply the weights times the bias gradients in the next level. So if this was level 1, L plus 1 would be 2, right? Which in our little model that we're doing here, that would have been the one, that would have been the final level, so we would have gotten the answers of the bias gradients directly from equation 1. So this is the weighted sum of the bias gradients of the next level give us the bias gradients in the previous level. Well, it's not just the weighted sum, it's times the output of the node times 1 minus the output of the node. This and this are the same. Now you might say, but Mike, there you were using J's there and you're using K's here. We were computing a result for node J here, so we were using the output of node J. Here we're computing for node K, so we're using the output of node K, right, in level L, because it was the bias gradient for node K in level L. So what's the whole thing? It's the weighted sum of the bias gradients times the output of the node times 1 minus the output of the node, and that will give you the bias gradients at intermediate levels. The last thing we need to do is to compute the weight gradients. So when we're talking about a weight gradient, remember JK is to node J from node K. So this is the weight that connects node K in, say, level 1 to node J in, say, level 2. So what is that weight gradient going to be? It's going to be the output of node J, of node K in level 1 times the bias gradient for node J in level the next one, so level of 2. Okay, so basically this is the weight that connects these two nodes together, node J and node K. It'll be the output of the source node and the bias gradient of the destination node. You're just multiplying those together. Okay. It's hard to visualize this when you're just starting out. So I tried to give you a visual representation of what's going on to help you keep all of this straight in your head so you can see the relationship. So here's our bias gradient equation again, right, for the final node, for the final layer, okay? And in this particular model, I'm saying, well, we had layer 4. So this, I guess, is a 5-layer network, layer 0, 1, 2, 3, 4. So if layer 4 is our last level, okay, and I said, okay, so let me break it down and show a particular example. So if this is node 0 and this is node 1, okay, let me compute the bias gradient of node 1, that's j equals 1, in level 4. Well, what is the bias gradient for node 1 in level 4? Well, it is the output of node 1 in level 4 minus the correct output for that node, right? So I'm showing this in green because these are inputs. So here I've color-coded it in the equation, right? What I'm computing is in yellow, right? It's the bias gradient for node 1 in level 4. That is equal to the output of node 1 in level 4 minus the correct output for node 1. That came from the one-hot vector, right? Then you multiply that times, again, the output for node 1 in level 4 times 1 minus the output of node 1 in level 4. So I've color-coded it here so you can see where things are coming from, okay? Next one, okay? What about computing the bias gradient for a node at an intermediate layer, okay? So now we'll be computing a value for a node, or a bias gradient for a node at level 3, right? If that's L, if L is 3, L plus 1 would be 4. So the way backpropagation works is you work from the last level backwards. So you have to start with the output layer, which we can do with equation 1, and then you can use equation 2, which we're now covering, to propagate backwards those bias gradients to intermediate layers. So what was the equation again? Oh, I get. So what was the equation again? Well, the bias gradient for node K and level L is equal to the sum of, I've got these weights here in the previous level times the bias gradients in the previous level. And it gets hard to keep up with all of those subscripts. But it shouldn't, because if you see it graphically, you see exactly what it's doing. I want to compute the bias gradient for, let's say, node 0 in level 3, okay? I don't have a reading directly of what the output for this guy should be. I have its output, it's A, what it produces right now currently, but I don't have a Y value. I don't have, well, I know what I got. What should it have been? Well, what we do is we say, I know the error for all of the nodes in the final layer, or in the next layer, because we're working backwards. So you start with the final layer. I've got the bias gradients now. I got these in the last layer from equation 1. Well, how about if I take the weight, okay, that connects this node 0 in level 3 to each of the nodes in level 4. And I just take that weight and I multiply it times the bias gradients and I sum these up. That will give me the weighted sum of the bias gradients for this node 0 in level 3. And that's what I'm doing here. I exploded it so that you can see the actual calculation. I blew out the summation. There were only 3 of them, so I was able to do that. And then, just like before, we have to multiply it times the output of this node times 1 minus the output of that node. And that's how you get a bias gradient for each node in the network. Because from the last level, 4, I now get all the bias gradients in level 3. Well, now that I have the bias gradients in level 3, I can apply it to level 2 and back them up to level 2 and then to level 1, right? So that's how I'm going to push things backwards through the network. The last thing I have to do is say, okay, those are my biases. What about my weights? Well, we said for the weights that what we would do is to get a weight gradient, we would simply take the output of the source node and the bias gradient of the destination node, and we would multiply them together. And so it's a very simple calculation here for the weight gradient. Now, of course, you got to do this for every single one of them, so that's where all those summations or all of those subscripts start coming into play, right? And if you were programming it, right, you would have basically loops that would be going through incrementing those things, because again, you have a whole every I'm only showing one weight here, but if I had 4 nodes here and I had 3 nodes here, right, you would have 12 weights that connected them, because this is connected to all three of these. This is connected to all 3. This is connected to all 3. This is connected to all 3. So 4 times 3 is 12. So I'm showing for one, computing a weight gradient for one weight, but you would have to do it for all of them. Okay. Questions. Let me pop over and look at questions. Questions. Let's see. Is the size of the training data based on the total input nodes, or how many things in your mini batch? The size of the training data has nothing to do with the input nodes. The size of the training data is how many digits do I have, right? So if we're doing the MNIST problem, I have 50,000 inputs. So, or actually, as we're going to see, there's 60,000 of them. But it would be all 50,000 of those is the size of the training set. If I break them into looking at 10 digits each per mini batch, then the size of the mini batch is 10. It's the number of examples that you have. Now, if I look at an example, each example digit is going to be 784 by 1 vector, because it's a 28 by 28 pixel grid. So for stochastic gradient descent, you're talking about mini batch sizes. For regular gradient descent, you would be talking about all of the data. So when we talk about what we're talking about there are this entry right here, right? It's for stochastic gradient descent, it's the size of the mini batch. It's how many items. Again, it's a very simple idea here, okay? You don't need advanced math to understand this idea. I want the average direction to go. So if there were 10 items in my mini batch, right, back propagation for every node in the network gave me 10 different opinions, weight gradients, of the direction that I'm supposed to go. Because every input's going to give me a slightly different error direction. Well, if I've got 10 opinions, what am I going to do? I'm going to take the average. So I sum up all of those weight vectors, and I divide by how many of them I had, 10. So now then, that gives me an average weight gradient, And how far am I going to move in that direction? I'm going to move in that direction by eta. Oh, and I have to remember I'm subtracting because I'm not going in the rate of greatest. This is the rate of greatest increase. I really want to go in the rate of greatest decrease. So that's all that's happening there. If we didn't have mini batches, I mean, the only difference between stochastic gradient descent and regular gradient descent is we have mini batches. Well, if your mini batch is the size of your entire training set, you end up with regular gradient descent. All right. So if I have 50,000 items and I decide that my mini batch is going to be 50,000, then these are the same thing. You're not going to get any improvement out of it, but the equations are the same. Okay, I hope that answered that question. Let's see, what kind of run times are we looking at while training on average in your experience? That's a good question. I see months of training. No, a few minutes. It depends on the speed of your computer. But a run might take you anywhere from, we'll see. No more than, say, 10 or 15 minutes, maybe 5 minutes, maybe whatever. So at this point, are there any other questions about those equations? I have not told you where they come from. I have kind of argued that they sort of make sense, right? The equations for backpropagation. And I've told you that the equations for backpropagation, the first two, the versions that I gave you, are dependent on using sigmoid neurons because they have the derivative of the sigmoid function in them. Okay, so if we were to talk about ReLU, they would have the derivative of the ReLU function in them. And we'll talk about that next time. But what I wanted to do at this point, and I actually think that I've done it at this point, excuse me, is at this point you should have all of the computational details that you need to be able to implement the MNIST program. So I haven't given you the mathematical conceptual reasons why these equations work, but I've given you the equations. I've explained how to compute them, and so you should be at this point able to implement the program. So I'm about to go over the programming assignment. Are there any questions before I do that? Any more questions before I do that? Okay, so let's look at, I lost my background. I took that really well, didn't I? I lost my background. I sound like the little 5-year-old in the back car, whining that it's taking too long. But hey, I have the magic of bringing SpaceX back. Let's see if it'll last another 5 minutes. We can't let Elon Musk down. Okay, so let's see. I want to share my screen again, and now I want to show you the assignment. Wait. Come on. So here is the assignment. Never figured that out. Okay. So here it is. This is assignment 2, the MNIST handwritten digit recognizer neural network written in Java. It's going to be due on October 29th at 9 a.m. So basically, let's see, the 29th, so that's 2 weeks and 2 days from now that it's due. This assignment will give you experience implementing and training a multi-layer, 3-layer neural network. Specifically, you will construct a Java program that recognizes the MNIST digit set. The data set in CVS format is available at blah, 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 and also on Moodle. Did we cover this last time? I don't remember if I went over this last time. I don't think I did I? Someone answer me. Did I go through this last time? I don't think I did.
I think you may have gone over it not terribly in depth, but you did go over it.
So I showed it to you guys?
I think so.
Okay. Well, I'm glad that you're not as sure as I am. So,
I remember seeing this.
Okay. I don't think I went over it in any detail. So I'll continue going through it. But I just had this deja vu, like, Mike, you've already talked through this. I think we at least talked about the data set. So anyway, it's on Moodle. The format of the data is label, then each of the pixels, right? Where the label is a digit 0 through 9, and each of these pix XYs is a 0 to 255 value, okay? So the data is organized as label, then pixel 1, pixel 2, pixel 3 for row 1, row 1, row 1, right? All 28 pixels for row 1, and then 28 pixels for row 2, and all the way to the last pixel, which is 28, 28, right? Each of these pixels is a value between 0 and 255. The only difference is this label is a value between 0 and 9 inclusive. So you've got a digit, 0 through 9, and then you've got all of your pixel values. So it's very important that in your code, when you read in the data, before you can use it in the backpropagation algorithm that we've talked about, this label has to be converted to a one-hot vector. So this label will be a number like 2, but you can't just use 2 to train. You have to convert 2 to be 0, 0, 1, 0, 0, 0, 0, 0, 0. You have to convert it so that it's a one-hot vector with a 1 in position, in the third position, the position for position 2, 0, 1, 2. Number 2, for best results, scale your pixel inputs to be a fraction between 0 and 1. In other words, divide each of the pixel values by 255. That's important. If you don't do it, your network's not going to learn. How do you know that, Mike? Well, because when Mike first wrote the program, he didn't scale it and it didn't learn. And he scratched his head and he said, what have I done wrong? I did everything right. And then he said, oh, well, maybe if I scale the input, it'll work. And magically it worked. A Python version of this program is going to be talked about in class next time. It's in chapter 1 of Nelson's book, Neural Networks and Deep Learning, which is available online. In other words, we're going to talk about Nelson's program. I present it to you as an example of a working program, just like I've presented the equations and graphical implementations of those equations to help you figure out what's going on. Do not try to take a Python program and transliterate it to Java. You will fail. Every student who's tried that approach has not succeeded in writing the programming assignment. Because some students say, well, there's a lot of math here and I'm not quite sure how it all works. So let me just take this Python program and convert it to Java. And you'll find that you will make transliteration errors, and because you don't understand the program, you won't know how to fix it and you won't know how to explain it. So do not do that. We'll talk about the Python program. You can use that to try to help you understand how a program can be constructed, but don't keep that Python program in front of you when you're writing your Java program. It'll just confuse you. Write your program from scratch, or you're not going to understand it, and you're not going to be able to debug it, and you're not going to get the programming assignment working. Okay? I hate to sound harsh on that, but every student who's tried to do it that way, they utterly fail. Because what they're trying to do is say, oh, it's too hard to figure out what's going on here. I'm just going to take this working program and convert it to Java. And you'll never debug it because you'll never know what it's supposed to do, and you won't understand the equations at a deep enough level to correct errors. So don't do that. What should your program do? Well, your program should implement a menu, right, that allows you to do some things. The first option is train the network. In training mode, your program should iterate through the 60,000, you've been saying 50,000, Michael. Okay. Here's the detail about the great 50,000 versus 60,000 debate. When I wrote my program, and when I first wrote my notes, I said 50,000 items in the training set. Why did I say that? Because there are 50,000 items in the MNEST data training set. But the MNEST training data set is actually divided into 3 subsets, not 2, 3. One is a training set, one is a testing set, and one is a validation set. We're not going to use the validation set. The site that copied the MNIST data from a horrible format that I looked at for probably an hour and said, I've got no idea how to read this crap in, to a comma-separated value system with a label and all of the little pixels. The guy that did that combined 2 of the sets together, the 50,000 training set and the 10,000 validation set, and left a 10,000 testing set. So in his data, there's actually 60,000 values in the testing set rather than 50,000. I figured this out a year or 2 ago because I was like, why are there 60,000? I only read the first 50,000 of them, so my program still worked. I just didn't realize there were 10,000 items that I never looked at until some student brought me their program and it had 60,000. I'm like, how do you have 60,000 items? There's only 50,000 of them. Then I looked a little deeper and went, oh, I've been talking about the MNIST data set in its original form, and I didn't realize that the guy who translated it to this comma-separated value actually put 2 of the sets together. So that's where the great 50,000 versus 60,000 debate comes from. So your program should iterate through the 60,000 MNIST training data set. I used a learning rate of 3, a mini batch size of 10, and 30 epochs, randomly initializing my weights and biases to the range -1 to 1. Well, I randomized my weights and my biases to -1 to 1 because my inputs are in the range of 0 to 1 and my outputs are in the range 0 to 1. And so I did this so that everything is in a similar range to help the thing learn. So my initial weights and biases are in the range -1 to 1, obviously using fractions. Don't use integers or it's a disaster, right? And scaled my pixel inputs again in a real range from 0 to 1. So that's the training data. Again, I used a learning rate of 3, a learning rate of 3, an ADA of 3, a mini batch size of 10, and 30 epochs. So I went through my 50,000, you're going to be using 60,000, items 30 times, okay, with initial weights and biases. After each training epoch, your program should print out statistics showing for each of the 10 digits, 0 through 9, the number of correctly classified inputs over the total number of occurrences of that digit. So, for 0, there were 4,907 zeros that it found over the 4,932 zeros that were in the data. Okay? For each of the 10 digits, 0 through 9, give me the number of correctly classified inputs. If it's 0, the number of correctly classified zeros over the total number of occurrences of zeros. So I did it for 0, for 1, for 2, for 3, for 4, for 5, 6, 7, 8, 9. All right? Secondly, the overall accuracy considering all 10 digits. In other words, after each epoch, the output should look something like this. So here's my accuracy was 49,646 divided by 50,000, which was a 99.292% accuracy that I got here. Now, I think this was after my 30th run, because I did 30 epochs. So don't expect to get 99 point something accuracy after having only gone through all of the data once, right? Note that I goofed thinking there were only 50,000 items when there were actually 60,000. You should use 60,000. That's why this number here is 50,000, because I only looked at the first 50,000 items, okay? Everything still worked out fine, but I skipped some data that I could have used for training. So training the network's the first thing you need to be able to do. Another thing your program should be able to do is load a pre-trained network. So what does a network know? Well, everything a network knows is just the weights and the biases. So those matrices that represent the weight values and the bias values, that's everything the network knows. It's like a core dump of a computer program, right? It's the actual the ones and zeros of everything that it knows. It's like an image, a memory image. So you need to be able to load one of those in, and without training, use that. Why? Well, because you're going to run the network multiple times in training mode, and maybe the first time you run it, you get a 95% accuracy on the training data. Okay, that's good, but so you save that off. Oh, I got a 95. And then you run it again and you get a 92%. Well, you're not going to get one that low, but let's just say you got a 92. Well, I'm not going to save that one because I already got one that's got 95% accuracy. And I run it again and maybe I get a 96% accuracy. Oh, that's better than the 95 one, so let's save that one, right? And then when you come to demo the program, one of the things I'll say is I'll usually say, okay, start up your program, load in your best network that you have saved off, right? So that's what number 2 does. It allows you to load in a set of previously saved weights from a file, okay? So either by training the network or loading in a pre-trained network, that's the first thing you've got to do, because you've got to have, before you can do anything else reasonably with it, you've got to have a network that knows how to recognize the digits. So either you're training it directly using one, or you're loading in a network that you've already trained. Item 3 in your menu is display the network accuracy on the training data. Obviously, that's only available after selecting 1 or 2 above. Right? Iterate over the 60,000 MNIST training data set exactly once using the current weight set and output the statistics shown above. And that's really pretty much where this comes from. I think that was my best run. So if you've got a previously, if you've trained it, or you've got a previously trained network that you loaded in, one thing is to say, how good does this network do on the training data? And it should do really, really good, because this is the data that you trained it on. So these are the 50,000 or the 60,000 items that you trained on over and over and over. 30 epochs worth, and each epoch is broken into 5,000 mini batches, so you updated the weights 600,000 times 5,000 times 30 times. You updated the weights and the biases, okay? So you better get a good accuracy there. But the real proof is number 4. Display the network accuracy on the testing data. This is the data that you did not train the network on. These are the 10,000 items the network never saw. How does it do on that data? Okay. So you iterate over the 10,000 item in this testing data set exactly once using the current weight set and output the statistics shown in one above. I'm not using backpropagation. I'm not teaching the algorithm or the network in either 3 or 4. I'm not adjusting weights or biases here. I'm just saying, how good does the network do? How good does the network do on the training data that it's already seen? And how good does the network do on the testing data that it's never seen? Does that make sense? That's what 3 and 4 are doing. They are showing you how accurate your program is on the training data and how accurate it is on the testing data that it's never seen after. Only run 3 and 4 after you've either trained the network or loaded in a pre-trained network. Number 5, well, obviously, if number 2 is to load a pre-trained network, number 5 should be save out a network. So if I've trained up a network and it's the best one I've seen, obviously I need to be able to save it off. So you can only save after you've done 1 or 2 above, right? And you're probably not going to save after you loaded in the same network, but you could. And a 0 to exit. So 6 options here, 0 to 5, 0 is exit, to exit the program. I would use just a console program for this if I were you. You can use a more complicated program that uses a graphical user interface if you would like. Now, what about some fun stretch goals? The stretch goals are to include your program or to extend your program to include the option to run the network on the testing data, not training data, testing data, showing for each input image a representation of the image itself, using ASCII art here, right? The network's classification. So this is testing case number, Mike is going blind, number 446, the 446th test case. The correct classification is a 6. That's the value, the label value that was associated, that a human came up with, that was associated with this bit pattern was a 6. So a human told the computer this is a 6. What did the network think the output was? The network thought it was a 0. Well, you can see why you might think this is a 0. It looks a hell of a lot like a 0 to me. But there's this little tail on there. So they made a 6, but with a really small tail on the top and a really big circle in the middle. All right? But you got to believe the human, because the human who wrote this said that is a 6. So the human is always right. That is, the human said this is a 6. So that's what the system thinks it should be. But it outputted a 0, and that label is, of course, incorrect. So run the network on testing data showing for each input image a representation of the image itself, that's this image, its correct classification, should have been a 6, the network's classification, it thought it was a 0, and an indication as to whether or not the network's classification was correct. It was incorrect in this case. I used ASCII art for the image in order to stick with a command line program and provide the ability to return to the main menu after each image. And you see down here I say enter 1 to continue, all other values return to the main menu. The second thing is similar to what we just did here, display only those images that were misclassified by the network. The vast majority of your images will be classified correctly. So if you only did part A here, as you'll see in a second, it would get very boring very quickly, because you'd see a 0, it would say, I think it's a 0, it was supposed to be a 0, that is correct. Here's an image of a 7. The user told me it was a 7, I thought it was a 7, that is correct. Here is a 9. The user told me it's a 9, I think it's a 9, that's correct. You get lots and lots and lots of corrects, okay? Because remember, we're talking about accuracies here that should be in the high 90s, right? So out of 100 images, it might be classified 2 or 3, something like that. So adding a flag so that it only shows you those that misclassified might be interesting. Additional requirements, you've got to develop your own code and work independently. Do not share your code. That is absolutely forbidden. I want to know what you know and that you can program this, not your friend who's also taking the class or some rando from the internet that you got a program from. Lifting a solution from the internet will not help you either. You must be able to explain how the code operates. And if you don't write it yourself, you won't be able to do so. It is far better to turn in a program, even if it only partially works, rather than some perfect program that you did not write and you do not understand. Okay? Part of what you're going to have to do is each of you are going to have to meet with me and present your program. We're going to meet virtually over Zoom, but I will have you run your program, share your screen, show me that it's working. We'll go in and we'll look at the code. I'll ask you to explain certain sections like, okay, where did you do thus and such? Show me the part of your code where you did thus and such. If you wrote it, you'll be able to go right to it and say, here's where I did that. Okay, well, tell me how that works. Well, it works like this and this, and then you'll begin to bore me after about 2 minutes. And then I'll say something like, okay, go and make this change to your program. Some little teeny tiny change. But if you wrote the code, you understand the code, you can go through and you can go, oh, okay, oh, it's right up here in this function. All I need to do is change this there. Okay, recompile it, rerun it, show me that it works. You must thoroughly document your program, including comments at the beginning of your main program with your name, your student number, the date, the assignment number, and a brief description of what the program does. Comments should also be present throughout the program to explain what each part does. Lack of appropriate comments can cost you up to 20%, 2-letter grades of your overall program grade. This is a gimme. Remember, you got to make at least a 50 on each of the programming assignments and term paper to pass the class. I'm giving you 20 of those 50 points right here if you just comment. On the other hand, if you ignore my instructions and you don't have a comment block at the beginning of your main program with your name, your student number, the date, the assignment number, and a brief description of what the program does, that will cost you 10 points. If you do not have comments present throughout the program to explain what each part does, that will cost you 10 points, a letter grade. So I'm giving you 20 points here that everybody should be able to get. You will be surprised at the number, maybe you won't be. I am always surprised at the number of students who lose points on this give me. Your program must be written in Java and run in Eclipse or from the command line. How are you going to submit the program for a grade? Your program should be emailed to me, mike@latech.edu, no later than 9 a.m. on Thursday, October 29th. The subject line should be CSC 475, Neural Networks Program, your name, where your name is replaced with your name. So, for example, if Susan Calvin were enrolled in the class, her email subject line would be CSC 475, Neural Networks Program, Susan Calvin. Who is Susan Calvin? I got to stop this so I can look. Who is Susan Calvin? Come on, this is important. Who is Susan Calvin? I have 40 students in this class, and no one knows who Susan Calvin is. No one. She was a character in. Sorry, say that again.
iRobot.
iRobot. Yeah, that's okay. Now, if people said iRobot, people were diligently going to Google and typing in Susan Calvin. Enter. Yeah, she is the. No, Susan Calvin is the character from the iRobot. Or from the robot novels, and yes, she's a character in the movie iRobot, but she's a robo-psychologist, so that's her character there. Okay, let's look. There were some real questions. We haven't quite finished the. Her character in the book are far better than in the film. You know, she's a. There's a robot story called Liar that is great, where a robot Susan Calvin it's the one where a robot could read minds, and basically robots aren't supposed to cause you pain, so because the robot could read minds, it told people what they wanted to hear because it knew that the truth would hurt them. So, like Susan Calvin, who was not an attractive woman in the books, there was some young robo-psychologist doctor or somebody that she thought was cute and had the hots for, and so the robot saw that she liked that, so the robot was telling her, oh, he's really attracted to you, blah 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 blah, but he wasn't. And eventually she made a move on him, and he rebuffed her, and that caused the robot to. She straight up killed that robot. Yep, that's basically what she did. She made it go, basically made it go insane and blow itself up. Anyway, beautiful stories. Okay, stretch goals are optional. Yes, let's get back to work. Do we need to have a specific format for saving and loading networks? Whatever works for you, Jonathan. Whatever works for you. Probably some comma-separated values that you read into the matrices that represent the weights and biases. Let's see. Let's see, stretch goals are optional, yes. They're worth 10 points, 10 extra points. Is it 3 layers, as in H1 and out? Yep, that is the way it is. There is 1 hidden layer, not 2. Will the IO menu be a make or break part of the code? You have to be able to run all the options that I gave you. I intend to do it, but I'd like to know if you prefer a working menu with a bad model or a functioning model with no I/O. That helps what I should prioritize. You have 2 weeks and 2 days. I think I wrote this thing from scratch in about 4 days when I first did it. And I think I told you the story that I hadn't written a Java program in over a decade, probably closer to 2 when I wrote it, other than little bitty snippets of code for, say, 325 and stuff like that. But a real program, I hadn't written one in forever. And I was able to do it at the ripe old age of, I guess I wrote that about when I was 57. If I can do it in 4 days, you should be able to do it in 2 weeks and 2 days. And you might say, yeah, but I've got other classes. Well, I have stuff to do too, believe it or not, like grading. Let's see. Okay, let's move back to it because I didn't quite finish. Got sidetracked by Susan Calvin. Sorry about that. You will be required to meet with me for approximately 15 minutes on either Thursday, October 29 or Friday, October 30th over Zoom to demo your program. Be ready to screen share your code, be able to compile it, be able to demo it. I haven't decided how to do our sign-up sheets yet. Usually I put a sign-up sheet outside my office door and people sign up for it. I could still do that, I suppose. I do occasionally come to campus, on the weekends or late at night when all of you little germ vectors are not there. Or maybe, I'm sorry, I shouldn't refer to my students as germ vectors. I apologize for that. That totally blew my train of thought. But if somebody knows of a good online tool, because basically I need a sign-up sheet, but I can't just put up an Excel spreadsheet and say, oh, go and change it, because if two people are trying to edit it at the same time, right, we need to have some sort of locking mechanism on it. So I haven't looked, but maybe there's something online that we can use so that if somebody else is accessing it, you get put in a waiting room until they leave. It needs to have an access queue in front of the document. If you cannot explain to my satisfaction how your code works or make simple changes to it, you will receive a grade of 0 for the program, which being less than 50% will result in a failure of the course. Now, don't panic. If you wrote the program on your own, you will find your 15-minute meeting to be exceptionally easy to get through. Some students just get so nervous meeting with the prof. You shouldn't get nervous meeting with me. You do your own work and it'll be fun, I promise, because you'll be able to show me what you did. Just don't try to pass off work you didn't do, because then it will be a very uncomfortable 15 minutes. And I've had a few students try to bluff their way through it, and I'm like, why are you even trying to do this? It's obvious. I wrote it. All right. No, you didn't. If you wrote it, show me how you did blah, blah, blah. Well, exactly. Be prepared to demo your program on your own laptop. I guess that's from when we were meeting in person. However, but you are going to be emailing me a copy of it, so I may actually have a copy of the program, and I may want to run it myself just to make sure that the source code you're showing me actually is generating the object code that you're running. Everybody wants to know, what's the grading rubric? What's the grading rubric? Which is funny, because used to, I would give the assignment and I'll say, well, I'll grade it. Now students want to know where every point is going to go. So 20% of those points will go for documentation. And we've already talked about that. 10% for the comment block at the beginning, 10% for comments throughout the program. Do you understand the program? If you can understand it, the student should be able to clearly understand what the program does and be able to explain the operation of any part of the program. If so, you get 10%. If not, you get a 0. So you basically understanding the program is required to pass. Modify a section of the program. Same thing, 10 points to make a small change, but 0 if you can't do it, because that means you don't understand the program. And again, I mean a small change. I might say something like, oh, increase your number of nodes in your hidden network from 30 to 50. Should be a one-line change if you know what you're doing. Right. Okay, now recompile the program and rerun. Let me see if it works. I/O behavior, 20 points. File I/O supported correctly, that's 10%. And in-user menu implemented correctly, 10%. So does that answer the question that I saw about what to concentrate on? On the other hand, if you don't have a menu, I don't know how you're going to be able to demonstrate that your program works, right, correctly, which is part of what we're doing here. Finally, 40%. 40%. The difference between a 60 and a 100 is based on accuracy. The numbers corresponding to the training data should have an accuracy of greater than 95% for 40 or more. If it's greater than 90%, 30, greater than 80, 20, greater than 50, 10%, less than 50, 0%. Another way of scoring partial credit, let's say you run into problems getting the program to work. Another way of scoring partial credit up to 20% is to show that your code can exactly reproduce the numbers provided in the Excel spreadsheet. What Excel spreadsheet, Mike? The one that I was going to show you, but I'm running out of time. Let me stop sharing. When to meet, if somebody could, or calendar. If you guys could send me links to those, that would be great. Sign Up Genius, that's another one. Okay, good, because these are all going to go away when I close this. So if you guys could email those to me, that would be fantastic. Okay, what does the damn thing look like when you run it? Okay. It looks like this. This is a 3-layer, well, this one I increased, 784 by 100 by 10 network of sigmoid neurons. The network is trained using backpropagation, stochastic gradient descent over a training set of 50,000 items divided into 5,000 mini batches of size 10. Again, you should be using 60,000 items. Don't do like I did. I'm not going to train it. Well, because it'll take too long, but I will load. Come on, what are you doing here? Here I loaded a network. So now then I loaded a network, and I can show you the accuracy on the training data. This is the data that it was trained on, so we would expect very high. I'm not training here. All I'm doing is just doing the forward pass, and you can see that I got 99.292% on this network. Okay? Now, what does it do on the testing data? This is the data it's not seen, that it was not trained on. Well, there are only 10,000 of those. It got 97.289. So you can expect it'll do a little worse on data it never saw before. That's fine. Okay, what about running it on the testing data, showing the data labels and images? That's 6. Testing case 1, the correct classification is a 7. The network output is a 7. That is correct. Here is a 2. It thinks it's a 2. It is a 2. It is correct. Here's a 1. It thinks it's a 1. It is a 1. It is correct. Here's a 0. It thinks it's a 0. That's boring as boring can get. So how about we look at just the ones that it misclassified? That's a 7. Well, it thinks it's a 7. Or no, a human said this is a 7. It thinks it's a 4. It's incorrect. The human said this is a 9. The network thinks it's an 8. Can you tell why? The human said this is a 4. The human was doing crack. The network says it's a 2. The human said this is a 6. The network said, I think it's a 0. That is incorrect. The human said this is a, what did the human say? The human said this is a 2. The network said it looks more like a 7 to me. The human said this is a 9. The network said, it looks like a 4. That looks like a 4 to me. The human said it's a 4. The network said it's a 5. I think the network was smoking crack on that one. Human said it's a 6. Network said it's a 0. Human said it's a 4. Network said it's a 9, etc., etc. But that shows you what this thing is supposed to do. If I had gone and started training the network, this is going to wipe what it knows. It's not going to erase the file, but it'll wipe what it knows. So this is running through all through the first 50,000 training items separated into 5,000 mini batches. It's going to run through all 5,000 of those mini batches before it prints a output. So, okay, it ran through the first one. It had 93.974% accuracy after going one epoch, one time through the 50,000 items. And then it'll take a while to get through the next one. By the way, this is a brand new computer, which is quite a bit faster than my old laptop, which might take several minutes to do this. And anyway, I think I go through 30 of these. I'm not going to go through 30 of these. I'm going to escape right now. If I'm able to escape right now, I don't know if I am. It's ignoring input. Anyway, that's that. One final thing I wanted to show you, that there is an Excel spreadsheet that I have built. We will go through the details of this Excel spreadsheet next time at the beginning of class. But basically, I have built a spreadsheet that takes in a very simple network. It has 4 inputs, all right, where there are 4 input examples, and my input layer has 4 input nodes. This is a 4 by 3 by 2 network, and basically what it does is it runs through epochs. This is the first epoch. It runs through multiple training cases in mini batch 1 and mini batch 2, but essentially what it does is it does the greens are random. It does a forward pass, then it comes back and does a back pass, and then it does a forward pass on the next input and a backwards pass on that input. And then using that, it updates the biases and the weights. And that is the revised biases and weights. That was mini batch 1. And then it goes into mini batch 2, where it takes in an input and it does the forward pass, then the backwards pass, blah, 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 blah. It just goes through. Why am I giving you this? I am giving you this because it's a known good. When you're trying to program this programming assignment, it can be very hard to figure out when you're not getting correct outputs. Are you doing something wrong with training, or have you gotten one of the equations wrong? You can write your program, and with a few little minor changes where you're not reading in data from the input file, you're reading in this data, you're using these X's, you're using these Y's, you reduce the size of the network from 784 30 by 10 to a 4 by 3 by 1. You should be able to change the size of your network really quickly. And then you have, instead of randomly generating the weights and the bias values initially, use these that I'm giving you the numbers. If you do that, every number that your program generates from every equation should exactly match what's in this spreadsheet. This is a way, it's a known good that you can use to make sure that you've implemented your equations properly. Like I said, next time we'll talk through it. Go ahead and look at it. It's exactly the equations that we've gone through that are implemented in an Excel spreadsheet. But I already see I'm 5 minutes over, so I'm going to end today's lecture here. If you have questions, I'll be happy to stay around and answer them. But I will see you guys on Wednesday. Take care. Hold on. Let me stop the recording. I will see you guys on Thursday. Take care.